Hi everybody, in this lesson we're going to talk about quantifying samples of matter in this class. This may be one of the most important lessons that you get for the whole first 2 months of class. So focus well on this one, please, and definitely jot down questions if you have them as they arise throughout the presentation. If you recall, I pointed out that there's a table in your book in a previous lesson about the actual masses of particles like protons, neutrons, and electrons. And those masses in units of grams are extremely small, okay? So we can't measure individual particles. We can't even measure I don't want to say handful, a few particles or 1,000 particles, because the particles are so small that even 1,000 of them would not really give us appreciable mass to be measured in our lab. So we need to define a quantity that will allow us to have a working amount of matter that we could actually see and handle. So you're familiar with the quantity a dozen, okay? And 1 dozen equals 12 objects. And we use the dozen to describe things like eggs, bagels, donuts, maybe the number of pencils in a box of pencils, okay? And it works pretty well for those objects. Those objects are not huge, but they're not super, super tiny. A scientist named Avogadro gave us the quantity that we will use in this class, and that quantity is known as the mole. Not this mole, okay, but I don't know why he called it the mole, but there you have it, okay? Kind of relates to molecule. So here we go. Here is how it works, and this is what it means. So if we look at the average atomic masses for these 4 elements, just sort of selected at random, helium, carbon, copper, and lead, you will see that if you look at the periodic table, and I usually go to 1 decimal place rather than keep all the decimal places that are on the periodic table, that an average carbon atom has a mass of 12 AMUs, average helium is 4.0 AMUs, etc. You also, I hope, recall from the previous lesson in Chapter 2 that these averages are a result of averaging the masses of the various isotopes, taking into account their abundances. Now, an AMU is a very, very small amount of mass, and so AMUs would not be measurable in the lab. However, it is possible to scale these quantities up to a larger pile of atoms, and this is what happens if we do that. What Avogadro thought and figured out was that if you take the mass of an individual atom and scale it up to a mass not in AMUs but in grams, it would represent the same number of atoms of each of these elements regardless, because a lead atom is 207.2 relative to a helium atom that is 4.0 in AMUs. If you scaled it up to 207.2 grams of lead, you'd be talking about the same number of atoms in 4.0 grams of helium. So just process that for a moment. This number of atoms in a mole is equal to 6.02 times 10 to the 23rd. This is known as Avogadro's number, okay? And it is mighty, mighty large, okay? And it is mighty, mighty large because atoms are mighty, mighty small. Now think back to a dozen for a moment. If I give you a dozen helium atoms, you have 12. If I give you a dozen carbon atoms, you would have 12. The number in a dozen is always the same, just like the number of atoms in a mole is always the same, 6.02 times 10 to the 23rd. However, the mass of a mole of helium is less than the mass of a mole of carbon, because carbon atoms have more protons and neutrons. And the mass of a mole of copper is larger still, even more protons and neutrons, and lead even larger because it has more protons and neutrons. So take a moment to read these 3 takeaways, please. Pause the video, read the 3 takeaways, and then turn play again after you're done with that. Okay, I hope you've processed that. I am going to call this mass of any element off the periodic table molar mass and abbreviate it MM, capital M, capital M. So let's just go through these elements here and see if we can say what we know about a mole of each of them. You will want to have access to a periodic table. It's going to be very important in this part of Chapter 2. So you can see that using the periodic table here, I have found the information about either one atom or one mole of atoms for each of these substances. This will be the preferred way to write this information, and that would be to write the molar mass in this manner as grams per mole. You could say grams per 1 mole, but the 1 is understood to be there whether you write it or not. And this is the way we will be writing molar masses for elements in this class. Using the periodic table, we can use the following information regarding carbon, and that is that this is the molar mass of carbon, 12 grams per mole. And if I multiply, I will get a mass of 24 grams of carbon if my sample were 2 moles. Now that kind of probably fits common sense. If 1 mole is 12 grams, 2 moles would be 24 grams, 3 moles would be 36 grams. So to some extent, you might be inclined to try and do this in your head. I'm going to encourage you not to do that. I'm going to encourage you to actually write these down and be systematic. For 2 reasons. It's going to keep you organized and track your units better. And the other reason is I need to see your work on all assessments and in all labs. So double the reason to write this down. In the second example, we're using calcium. Looking on the periodic table, you can see that the molar mass of calcium is 40.1 grams per mole. The work here results in 0.18 grams of calcium. In our last example, we're talking about aluminum. According to the periodic table, aluminum has a molar mass of 27.0 grams of aluminum for every 1 mole. Moles will cancel. This turns out to be a rather large answer. I'm going to put it in scientific notation. 1.5 times 10 to the 6th grams of aluminum. If you are unsure of how to enter a number like this into your calculator properly, bring it up in class and I'll give you some instructions. It does depend a little bit on the particular calculator you're using, but I'll give it a shot. We can also use the molar mass to calculate in the other direction. That is, start with grams and determine how many moles would be in a sample of that many grams. So let's set these up and go through them one by one. In the first example, the molar mass of helium from the periodic table is 4.0, but notice in this example, I need to invert that relationship so that grams is able to cancel. It is still true if I invert it, just as a metric conversion is true whether I write 100 centimeters over 1 meter or 1 meter over 100 centimeters. So the molar mass can be inverted as needed to do unit cancellation. In the second example, magnesium has a molar mass of 24.3 from the periodic table. That goes in the denominator, cancel out the grams, and we end up with 80.0 moles. In this example, I've thrown you a little bit of a curveball by giving you milligrams instead of grams. However, that's no big trick. You know how to convert. And so first step I do is to convert the milligrams to grams, and the second step is the mole conversion using the molar mass from the periodic table. And we get 1.1 times 10 to the minus 4 moles of silicon, or 0.00011 moles of silicon. Either way is fine. So here's the quick summary of how to do both of these things. In order to convert from moles to grams, what you're going to want to do is multiply by molar mass in the numerator and moles in the denominator. So grams per mole. And that molar mass is always found on the periodic table. If you're going from grams to moles, you're going to be doing it the other way. You're going to flip that ratio over, and it will be 1 mole per whatever the periodic table says the molar mass is. Write this down somewhere in a place where you will have it handy. You are going to use this all year long. So here's a set of examples. I'd like you to pause the video at this point and take the time to do these 6 examples in your notebook. And when you are done, restart the video and you can check your work. Okay, so I truly hope that you took the time to work these 6 examples out. And here you see the answers. So check your work against mine. And if you see any mistakes, let me know in class. I'm double checking and it looks okay, but you never know. I do crazy things now and then. So that's it for our moles and grams lesson for today. Very important lesson. Thanks for watching.